So for a general linear map T, it's always the case that T of 0 is equal to 0. And this in the book is listed as theorem 311. But the proof is very simple. The book gives one proof. Here's another one. T of 0 is the same thing as T of the scalar 0 times any element u of the vector space. And then I can pull the scalar out. And then by a previous theorem in the book 1.30, this is going to be equal to 0. Okay, so the upshot here is that since 0 is an element of any vector space, the equation TV equals 0 always has a solution. And that solution is the trivial one. It turns out to be a very interesting question to ask about whether or not the trivial solution is the only solution. And so we have a definition to formalize this. We say the null space of a linear transformation T is the set null T defined by being all elements of V that T sends to 0. And so from the definition right here, you can see that the null space of T is a subset of the domain of T, so it lives in V. Okay, and we have basic proposition 3.14. Null T is a subspace, which you probably guessed because I was calling it the null space, right? Dead giveaway. So this is a subspace of the domain of T. Okay. And the proof just comes by straightforward checking the closure properties. So let's see. So we already saw that 0 is always included. So now let's check closure under addition. And pick U and V to be elements of the null space of T. Okay, so then if you were working through this proof on your own, probably the first thing to do is say, okay, let's pick a couple elements of the null space. And since we've picked a couple of the things here, then we write down what we know to be true for them. So in view of the definition that we just wrote down here, we know that TU is equal to 0 and TV is equal to 0. And so we have to figure out how to use this. So, in fact, you know what? Here, I'm not even going to include this part as part of the proof. This will be a thought. Okay, so my thought is going to be, whoops, in green. That's my version of the hypothesis that I'm going to be using in this proof. Okay, so you whoops. So keep that in mind and think about a way to make use of that thought. All right, so we have T of U plus V, and we have to show that this is an element. Sorry, we have to show that U plus V is an element of the null space, which means we have to show that T applied to it gives you 0. All right, So what do? Well, we apply t to it and then see what we get. That's the thought process. Okay, and so when faced with this expression, t of u plus v, there's so little on the board that I don't really see anything that I can do with this other than just use the linearity of t. But then when I see tu and tv appear, I go, I just had a thought that tells me about tu and tv. So I know that I can replace these with 0. And now, looking from start to finish here, I can see, so u plus v is something that gets sent to 0. Therefore, by definition, u plus v is an element of the null space of T. All right. Then we do the same thing for closure under scalar multiplication. So pick some scalar lambda. And then now I'm going to do the same thing. I'm going to look at T of lambda u, because I want to see that lambda u is in the null space, which means I need to check that T of it goes to 0. So I just apply T to it and see what we get. And again, I don't really see anything that I can do with this expression except use linearity of T. So I pull out the lambda, and then I go, I chose u back here to be in the null space of T, so I still have this thought going on. And so this is lambda times 0, which is 0. So now we've checked both closure properties, and we know we've got a subspace. And so this is, I guess, by, 134.